All right, let's do a refresher here of piecewise defined functions. So a piecewise defined function is defined by more than one rule. So you'll be given some specified interval for x, and on that specified portion of the domain, you'll be given the rule for how you would compute the y values. So for example, for this function here, think about what f of -1 equals. So the way we work with this function to find a particular y value is we identify which of the cases our given x falls into. So -1 is between -2 and 0, so that is the rule that we have to use to find f of -1. So it would be negative x squared, so negative, our input is -1. So that becomes, when we square -1, we get 1, so it's -1 or just -1. So in this case, f of -1 is going to be -1. All right, what about f of 1? Okay, well, 1 falls into this interval here from 0 to 2. So that means we have to use this rule to find f of 1. So we replace x with 1, so we get 3 times 1 plus 1, or 4. So f of 1 is going to be 4. All right, 0, f of 0. So you'll notice that 0 is in both spots. However, you have to look at the one that actually includes 0. That one is strictly less than 0, so we have to go to this one where x is bigger than or equal to 0. So at the breaking point, you have to figure out which one includes that x value. Okay, so it's going to be equal to 3 times 0 plus 1, or 0 plus 1, which is just 1. All right, so that's the way we work with piecewise defined functions to find particular y values. All right, let's sketch the graph of this piecewise defined function. So it's going to go from x equals -2 to 0 for the first piece. And so what that graph is going to be is it's going to be the graph of y equals -x squared. So what does that look like? Well, it's a parabola that opens downward. So don't use pen if you're taking notes. Don't use pen because I'm going to be erasing part of this. So here's the graph of y equals -x squared. This parabola that opens downwards. All right, we're not going to use the entire parabola though. It's just the portion starting at x equals -2 and then ending at x equals 0, but because of this strict inequality, we won't put a solid point where x equals 0. We'll use an open circle, okay? So here, this here was just to give me a ballpark start. So starting at x equals -2, I actually will find what the y value is. So -2 squared is -4. So here I'm going to erase this part and have the point -2 comma -4. All right, so it turns out that it wasn't all that bad, but I do need to erase this. Because the graph has a hard stop at x equals -2. So this portion that I've drawn is actually outside the interval, x interval from -2 to 0. So I'm going to actually erase that. So that's not going to be included. Okay, so this is one way you can get the graph of a piecewise defined function, is you can start by graphing the whole rule, ignoring this restriction, and then incorporating the restriction as I am right now. Okay, so I start at -2 and have this parabola that opens downwards, and then I have an open circle at 0. All right, so now I pick up with the next rule. So the next rule is y equals 3x plus 1. So that is a line. That's a line with a y-intercept of 1 and an x-intercept of -1/3. So ballpark right around there. So I would draw the whole line. I'm going to erase it though, so I draw the whole line. Only then I need to take into account the fact that x starts at 0. So none of this is actually part of our graph, so I'll erase it. As you work more with these, you'll get faster and maybe not actually need to draw that portion, but at the beginning, while you're getting used to it, then you should draw the whole thing so that you know you're getting the key pieces of information in the right spot, okay? Namely, for, say, if you have a parabola, you want to make sure if the vertex is supposed to be in the given interval, that it's actually showing up in the given interval. All right, so here we have a line segment that starts at 0, 1. So because 0 is included here, we make it a closed circle. And then all the way to x equals 2. So here's x equals 2. And the y value that goes with 2 will be 3 times 2 plus 1, or 7. So I have to actually extend this all the way up to 1, 2, 3, 4, I'll call that 5, 6, 7. Okay, so 2 all the way to 7. And it's a closed circle, and it's that line segment. Okay, so right there, this is the graph of that piecewise defined function. Okay, why don't you press pause while you work on this example? Okay, so my convention, if I don't label the x-axis, the convention is that each one of these, the convention would be that we start at 1, and then that's 2, that's 3, and so on. So if you want those to, if you want that to be a different scale, that's when you actually really need to label it. All right, so we start with y equals x squared minus 3. So y equals x squared minus 3. It's going to be a parabola that is shifted down 3 units. Okay, so we should find out what the values are. Okay, so again, here's a ballpark sketch of it. Then I'll get more precise in a little bit. So I want to find out what the y value is that goes with x equals negative 2 and the y value that goes with x equals 2. So x equals negative 2, then we get negative 2 quantity squared, which is 4, minus 3 is 1. So when x is negative 2, the y value is 1, and that's going to be a closed circle. Then it's going to go down there, and then it's going to grow all the way up until x equals 2. So when x equals 2, we get 2 squared minus 3, so that's 4 minus 3, which is also 1. Right, so that's the portion of the graph that goes with the first rule. So I'll erase any bit that wasn't needed. All right, so now let's pick up the second rule. So the second rule is a line with a y-intercept of negative 2 and an x-intercept of 2. Okay, so it would go something like this. Only, so now I kind of have the idea, so now I will go ahead and plot that. Okay, so when x is equal to 2, then I get 2 minus 2, which is 0, so I would actually have an open circle here. Then when x is 3, I get 3 minus 2, which is 1. I'll have a closed circle there, and now I just connect those dots. Okay, so notice that sometimes, so this right here is the graph of our function. So note that sometimes you'll have an open circle on top of a closed circle. So an open circle and a closed circle at the same spot. So at the same location. The closed circle wins because if that y value exists for some x, it exists for the whole function. Okay, so the circle gets closed in that case. So for example, if instead of being x minus 2, if that were x minus 1 instead, then when x is equal to 2, we would get 2 minus 1, which is 1. Then that would be an open circle right there, where I had that closed circle. Only open circle, closed circle in the same spot, closed circle wins. So, and then when x is 3, we would get 3 minus 2. Sorry, when x is 3, we would get 3 minus 1, which is 2. So that's what the graph would actually look like if it were x minus 1 instead. Okay? But it's not, so I'm going to erase it. So again, open circle and closed circle in the same spot. Closed circle wins because there is a y value that goes with that point, or that goes with that x value. Right? So let's now solve the equation f of x equals 0. So if we look at the graph here, we can see that there are 2 spots where f of x equals 0. So f of x is not 0 there. F of x is 0 at that portion of the parabola and at that portion of the parabola. So we see the first rule actually gives us where the function crosses the x-axis. So we can go to that first rule. So we get x squared minus 3 equals 0. Then solve that, we get x squared equals 3, or x equals plus or minus the square root of 3. So those would be the 2 solutions to f of x equals 0. All right, the last thing I want to touch on is the notion of continuity. So a function has a discontinuity at an x value if there is a break in the graph at that x value. Okay, there is a much more formal definition of a discontinuity, but this is the starting point when you're in Algebra 2 to just get the notion of having a break in the graph. So for example, here if I'm tracing along the graph, fine, I get to here, I actually have to lift my pencil to continue. So that means there's a break in the graph. So this function has a discontinuity at x equals the x value of 2, which is where the break occurs. Just touching on that, polynomials are nice functions, just powers of x. So we would say that there's no break in the graph of any polynomial. So polynomials don't have discontinuities. The other way we could say is polynomials are continuous on negative infinity to infinity. So that's a property that actually makes polynomials really nice functions. Okay, they don't have breaks in their graphs. They don't have any discontinuities. In other words, they are continuous on negative infinity to infinity. Right, so that's the basics of the notion of continuity. Again, look at the graph. If there's a break in the graph, you have a discontinuity. If there's not a break in the graph, you don't. It's continuous everywhere that it's defined. Right, so take a look at this graph from the last problem. Think about whether or not that one has a discontinuity. The answer is it does have a discontinuity, so discontinuity at x equals 0, because if we traverse, it's at 0 that we have to pick up and continue the graph.